Okay, welcome everybody. We're happy to have Shashank Kanade here, who will tell us about principal characters of standard A2 upper 2 modules.
Thank you so much, Josh and Corina, for inviting me. There is a bit of a construction going outside, so in case there is some noise, I already apologize. And I think it should be okay if anyone wants to just stop me and ask questions. I don't know how you do it in, yeah. Because I don't think I'll be able to view the chat very effectively. All right, so let me get started. So I'm going to talk about principal characters of A22 modules. A22 is an affine Lie algebra. Perhaps the next simplest after A11. So it's got two nodes in the Dinkin diagram and so on. Anyway, I'll talk about the characters more than the actual algebra itself. So let me get started. Let me start with so the characters are going to be related to integer partitions and Q series. Let me start with partitions. So partitions are easy. It's just you take a positive number and then you write it in terms of other positive numbers. The order doesn't matter. For example, here 9 is 1 plus 2 plus 3 plus 3. If you think about it a bit, the generating function for the partitions is just this infinite product, where you're supposed to expand each term as a geometric series in the region q less than 1, but I'm not going to bother with analytic properties. It's just going to be all formal. One thing which I should, so everything's going to be formal, as I said. One thing which I should mention is this notation is very, very crucial. It's kind of like factorials, but in the Q world. So these are called the Pochamer symbols. So you take a parameter A, and then you take a base Q, and the subscript J tells you how many products you have. So you start with 1 minus A, and you go to 1 minus A Q to the J minus 1. So total there should be J terms, which is the subscript here. Okay, and you can plug in anything for A that you want. You can even take the base to be Q squared, Q cube, or whatever. And sometimes it may be convenient for me to have a bunch of these parameters and then a single base. So I'll just multiply these things out. You can even take the subscript to be infinity. So I'll use this notation heavily, so it'll be good to remember that, but I can remind you anytime you're confused. All right, so let's go ahead. I want to talk about identities of Rogers-Ramanujan types. So what are these? These are identities about restricted partitions. So let's review the first Rogers-Ramanujan identity. It's the partitions of n in which adjacent parts differ by at least 2. I'll take an example in a moment, but turns out if you count the number of such partitions, then they end up being equal in number to the partitions of the same n where every part is congruent to 1 or 4 mod 5. Okay, or plus or minus 1 mod 5. Now there is no 5 on the left-hand side of this identity, but there is miraculously a 5 on the right-hand side of the identity, and that's one of the things about this. So the left-hand side and right-hand side are almost miraculously equal. So here is an example. You look at partitions of 9, where here there are no adjacent parts, so everything is good. And you can see that on the left-hand side, the adjacent parts have difference at least 2, like 1, 3, 5. You're not allowed to write less, I think, 2 plus 3 plus 4, because 2 and 3 would be very close together. You should have at least 2 as a difference. And on the right-hand side, I have partitions of the same 9, but where now every part is congruent to 1 or 4 mod 5. And there are 5 of these, 5 of those. They are equal in number. As sets, they are not the same, but they're equal in number. And this holds for all numbers in place of 9. Okay, let's look at generating functions. So let me have the generating function of partitions with difference 2 condition. And so count how many partitions there are for n, and then multiply with q to the n, sum it all up. And the Rogers-Ramanujan identity says that that's equal to this product, where on the right-hand side, I have only those exponents of q, which are 1 or 4 mod 5. So 1, 4, 6, 9, and so on. It's an infinite product. Now, turns out there is a better way to write this sum side on the left-hand side. So that's written like this in the middle line: 1 plus q over 1 minus q plus q to the 4 divided by a Pochamer, and it goes on. The general term is q to the n squared divided by that Pochamer of QQn. And the product is the same. I have not done anything. So it's a bit of an exercise to go from the partition theoretic sum side to the sum side that I've written here, but it's a nice exercise. We'll do it. And there is a terminology for these. So if I express it in terms of partitions, I'll call it partition theoretic sum side. The middle one is typically called the analytic sum side, and the right hand side is always called the product. All right, so let me just give a brief overview of how you go between that partition and the analytic sum side. But really, this talk is about that analytic sum side. So let's take a partition that has difference 2 in adjacent parts, and let's look at a partition that has length 4, just as an example, okay? So take any partition with length 4 that has this difference 2 condition, for example, 1, 3, 6, 8. Yeah, write down its Ferris diagram, which is just dots, and successively remove 0, 2, 4, 6 parts from each of the parts, all right? So I remove nothing from 1, remove 2, remove 4, remove 6. And because you have a difference 2 condition, if you remove this, it's called removing the 2 staircase, you will get an honest partition, right? You'll get something that has only weakly increasing parts. And it's 1 plus 1 plus 2 plus 2. And this process is reversible. In other words, the Rogers-Ramanujan partitions of length 4 are in bijection with just partitions of length 4. Now take the generating function of partitions with length 4. It turns out this is that. Okay, so X counts how many parts there are, and it's an easy exercise to know that that's the generating function. And now you put back a staircase, which means that you add 2, 4, 6. So Q to the 2 plus 4 plus 6 to that. At the level of generating functions, you get that. And of course, you now see that this 2 plus 4 plus 6 is just going to be twice the triangular number. That's where the square in the numerator is going to come in. And you get this as the generating function on the left-hand side. So now you add up over all possible lengths. You don't have to stick with length 4. And at the end, you don't need this X. You can set it to be 1. And that's, if you do that, the left-hand side ends up being exactly what I told you, Q to the squares divided by the bookhammers. Okay, so I don't need this a lot, but the point is that it's not always, I mean, this is easy in a way, but it's not always that easy to go between partitions and analytic sum sides. All right, so this is the first Rogers-Ramanujan, as I said. Now you can, so I said there is a pair, I guess I said. So there is another one. So where is that? So I'll give you an experimental way of looking for it. So deform the exponent of Q by a linear term, C, so C times N, where C is unknown at the moment, and test whether for any C this ends up being a product. Okay, and turns out you will see only one C that works. It's C equal to 1. And you get another identity. And now the product side turns to plus or minus 2 mod 5. Okay. And now you can reverse engineer the process, and you can attach the partition theoretic description to the left-hand side. And it's very similar. Adjacent parts differ by at least 2. And the smallest part now ends up being at least 2. So you disallow 1 to be a part. And the right-hand side is easy to figure out what it is. It's partitions in 2 or 3 mod 5. Okay, so this is a pair. So this is another feature of such identities. They occur in sets. And another good thing about these is that this is not an isolated phenomenon. There are lots of identities of this type. So if you want to change this mod 5 to something else, you can do that. And the mod 7 identity, there exists 3 of them. And now instead of adjacent parts, you require parts at a distance to be differing by at least 2 and so on. And they are equinumerous with something mod 7. And again, you can figure out a generating function. Now it involves 2 summations. There are more identities at mod 7. It's fine. I mean, at the moment, it doesn't matter what they are. And in general, for odd moduli, you get what are called Andrews-Gordon identities. Please remember this name. It's going to come up quite a bit. And for even moduli, you get Anderws-Bressoud identities. Okay, so exactly very nice generalizations of Rogers-Ramanujan. But on the even side, there is more subtleties, which I'm not going to go into. Okay, so for me, these are going to come from characters of affine Lie algebras. So this goes back to the work of Lepowski, Wilson, Feingold, and Milne. So let G be an affine Lie algebra. And let's take the simple roots for G, alpha I. And let's take an integrable highest weight module for G. These are what I'll call the standard modules with highest weight lambda. Now, for all such modules, there is a canonical integer attached to, or positive integer attached to them. It's called the level. I'll denote it by L. It's not positive. It could be 0 also, but anyway. And we look at the character, as you always do in representation theory. And turns out here it lands in this formal power series ring with just e to the lambda is just, it denotes the highest weight, but we are not going to need that part. I'm just going to normalize the characters by deleting that part, and they are going to land in this space. It's a formal power series ring. And what I'm going to do is I'm going to principally specialize it. So first I'll delete this factor, but then all these formal symbols, I'll specialize them all to Q. That's called the principal specialization. So again, I took a standard module and I looked at its character, and I then substituted one single parameter for all the unknowns there. And the theorem is that the principally specialized character, the ones that I showed you, these are infinite periodic products of the kind that you saw in Rogers-Ramanujan. So Rogers-Ramanujan was periodic mod 5, everything repeated mod 5. So these will also be periodic mod something, depending on the level and the algebra you take. So this comes from Wildcat's character formula and Lepowski's numerator formula. And let me show you an example. If you take the simplest algebra, A11, SL2 hat, then for the level 1 modules, there are 2 of them. You see that the character ends up being this, which is partitions into odd parts if you are quick enough. I'll denote this by FQ. Yeah, it comes up, it's going to come up again in a minute. And if I look at level 3, there are 4 integrable modules at level 3 up to isomorphisms. And because I'm doing principal specialization and there is a Dinkin diagram automorphism for SL2 hat, there is an outer automorphism that equates the characters of 2 modules at a time. And if you look at these 2 modules, their characters are exactly the same, principal characters, and they end up being this factor times, now you know how to recognize this, that's the second Rogers-Ramanujan product, yeah, congruent to 2 or 3 mod 5. If I look at the other 2, their characters also end up being the same, and you see this same factor coming up, and then the first Rogers-Ramanujan. Okay, so the Rogers-Ramanujan type identities are going to come for me when you look at characters of integrable modules and after you delete this fudge factor, as it's called. Okay, so that's the key for me. So these are what are called the principal characters, where I delete the fudge factor. Okay. So I don't want to say principally specialized characters where you delete the fudge factors. I'll just say principal characters, and that's this pink part here, or magenta, I guess. Okay, let me go ahead. So as I said, these product sides are immediate from Wildcat's character formula and Lepowski's numerator formula. It's literally at the push of a button. There are programs that do it for you. And you remove the fudge factor. That's not going to play a role at the moment for me. And the corresponding sum sides, there is the beautiful story of building a basis actually of the modules in question using Lepowski-Wilson's Z algebras, which at that time there were no vertex operator algebras, but these are really vertex operators, twisted vertex operator, as they came to be understood within a few years of their invention. Yeah, so the sum sides are going to come from a completely different mechanism from the product sides, and that's one of the nice things about these, is that they really illuminate the structure of the modules because they come from different mechanisms. So this is one way to get identities out of modules of affine Lie algebras. There are other many ways of getting these. There is a lot of work and Prims. They have been able to get a lot of identities. There is recently a work by Johan Doos and Isaac Conan based on crystal bases and so on. There is other ways of getting these by using Hall-Littlewood polynomials, and this is what Ole Warner has been doing for a lot of years now. But anyway, I'm going to concentrate on the one I told you. Okay, so here's a bit of a list of what I know about these characters. So as I said, A11 at level 3 is Rogers-Ramanujan. This was Lepowski and Wilson's work. They proved it using completely just A11. At A11 odd levels, you get Gordon-Andrews identities. And again, this is the work of Lepowski, Wilson, and Merman Primts. At even levels, you get Anderws-Bressoud. And by rank level duality, you end up getting the same identities at a lot of other at a lot of other algebras. For example, AN1 at level 2, you get again Anderws-Bressoud and Andrews-Gordon, but then it depends on whether the rank is even or odd. Same happens with CN1. So this is, I think, work of Mishra. F41, that's Marley Mandia. It's Rogers-Ramanujan again. G21, Rogers-Ramanujan again. So for a lot of low-lying cases, you see Rogers-Ramanujan, Andrews-Gordon, they come up. So is there anything new? Well, of course, there are lots of affine Lie algebras out there, infinitely many, in fact. So let me start with the next one. Okay, turns out A22 is again Rogers-Ramanujan, but it ends up being dilated by Q goes to Q squared. A22 was a new identity at that time when it was discovered by Caparelli. No one had seen it before on the Q series world. It was proved by many techniques afterwards. A22 level 4 is extremely complicated Nandi's identity, and it was recently proved by Takegiku and Tsuchioka. It's a very fascinating development because Nandi's identities, I'll show you, they're very complicated. They also conjectured some identities for A22 at level 5, level 7. And at the Q series level, A22 for all levels, for one module, the analytic sum sites were known by the work of McLaughlin and Sills. But at the moment, it's not clear whether these sum sites are related to the actual bases of these modules. And at all levels, 2 modules were given by Sills 8 years later. Okay, there are other series of algebras where it's also something new. So A52 at level 2, it's Golnitz-Gordon. You can actually demonstrate it using bases. At A92, we discovered some new identities, and they were quickly proved, very surprisingly, by Brinkman, Jennings-Schaefer, and Malberg. At A13-2, recently, there is a new conjecture by Takegiku and Tsuchioka. It's not proved yet, as far as I know. And at a completely different series, D43, there were some conjectures that we made which are not yet proved. All right, so let me just quickly show you the Caparelli identity. So it's a mod 6 identity. It's really a mod 12 identity, but it folds back into mod 6. That's the product side, whatever. And you see things that are very similar to Rogers-Ramanujan. Smallest part is not 1, so it has to be at least 2. Adjacent parts differ by at least 2. And if they differ by exactly 2 or 3, then their sum has to be divisible by 3 or something like that. Okay. So anyway, there are variations on the Rogers-Ramanujan theme, and there are other identities. There is actually one more identity because there are 2 modules at level 3 for A22. At the moment, the description doesn't matter. I just wanted to give you a flavor of it. And there are lots of proofs of this particular identity. All right. This is the level 4 identity for Nandi. Most of it is tame. You know, if the difference is something, then something happens, and so on. But the real kicker here is there is an infinite list of conditions that you see. So if you look at the adjacent parts, take the difference, yeah, write down all the differences that you have, and none of the following are supposed to be sub-words of this list of differences. So for example, you're not allowed to have 033 as a consecutive difference, 0323, and ad infinitum. So this was something completely new. No one had seen this before. And recently this was proved. It's very surprising that anyone was able to prove it, but it's been proved. Anyway, so the point is that it's getting harder to do algebra to get new identities by doing this procedure. I mean, it's going to lead to many complicated things like that. All right. So let me now tell you what these characters are for A22. So pick a level, that's a positive integer. Turns out there are these many modules, roughly half the level. And they are parameterized by two integers, S0 and S1, and the level has to add up to S0 plus 2S1. That's just coming from just simple considerations of characters. Sorry, for the level. Um, Now, what I want to do is I want to remove that fudge factor, right, in the character that I told you before. And that corresponds to looking at the space of highest weight vectors with respect to what is the principal Heisenberg subalgebra of A22. And then I'll take the principally specialized character. Okay, so I want to do two operations. First operation removes the fudge factor. The second operation is what you know, it's principally specialized character. Now it's best to shift everything by rho, right, which is half the sum of positive roots in the finite case, but you have an appropriate modification in the affine case. So that corresponds to changing these integers by 1. And then the characters look like this. Okay, so take a moment. And you see that it is periodic modulo 2 times S0 prime plus 2 times S1 prime. Yeah. Now remember, S0 and S1 were related to the level. So if you just decompile this very quickly, you'll see that they're periodic mod 2L plus 6. Okay, so you'll get products that are periodic mod 2L plus 6. So for Caparelli, it was level 3, remember. So it's periodic mod 12, but for that particular Caparelli, it folded into being mod 6. All right, so that's the characters. So these are the products. I want to get the sum sides. So here is the level 2 example. It ends up being just a dilated version of Rogers-Ramanujan. Q goes to Q squared. If you stare at it for a minute, you'll see exactly what I'm saying, but I'm not going to spend time on that. That's Caparelli, as I told you. It's really mod 12. All right. Okay, so now let me tell you how to get the sum sides. It's possible I may not get through the talk, but that's completely okay. This is one section which I would love if I can put it across. It was something new to me, and it's a little complicated to understand, but actually it is not. It can be understood very easily if you just have Maple or any other computer algebra program at your disposal. Okay, I think there is someone in the waiting room. Should I admit them? Okay, all right. Okay, so there is this mechanism of Bailey pairs on the level of Q series. And Bailey in, I think, 1940s or something, found the main machinery behind Rogers' proof of Rogers-Ramanujan identities. So Rogers had actually proved all these identities, but his work was forgotten, turns out. And the key to it is what he called the Bailey transform, which at the end of the day is just a matrix equation. So you have a vector and it's m times, m is a matrix times another vector, and you have another pair of such things. And it's just a really stupid looking thing. But that's not why it's important. The importance comes from putting smart substitutions in place of this gamma and delta and also the m. Okay. So as such, this is just a plain easy matrix equation, but the power comes from substituting good things in it. And Slater, who was a student of Bailey, I think, in 1950s discovered such Bailey pairs. So these are called Bailey pairs, which are related by this equation, beta and alpha. And she deduced about 130 identities of Rogers-Ramanujan type. And so this putting smart things in here is encoded in what is called the Bailey's lemma. And what it does for you is that it gives you, starting with old Bailey pairs, it gives you new Bailey pairs. That's one thing it does. And secondly, it can also give you identities. And so this mechanism of getting new Bailey pairs is usually termed as what is called the iterative power of the Bailey machinery, and it's discovered by Andrews and Fowler independently. And then there are other things that are important for us, which some things called the base change. I'll explain what this is, and then there is a base shift. Okay, so let me explain what this business is. So everything depends on a parameter A, and consider this infinite lower triangular matrix. So it's like that. It's typically denoted by N and R. So N is the row and R is the column. I know it's unfortunate, but yeah, that's the notation that people use. And so you just consider these poke hammers. Okay, now see that if R is bigger than N, then you're getting a negative number as this subscript, in which case you just define all of this to be 0. Okay, that's why you get a lower triangular matrix. And let's write down a few rows, and that's exactly how it looks. Yeah, you'll see pokehamers in the denominator. And so the indexing starts from 0, n and r equal to 0, right? So the top corner is just n equal to 0 and r equal to 0. Yeah, is that okay? Yeah, it's just an infinite lower triangular matrix. And two sequences of Q series form a Bailey pair with respect to that base A. Remember, everything depended on a parameter A, if they are related by this matrix equation, period. Yeah. And so if you decompile what this is, so I'll denote it by shorthand. Beta is MA times alpha. If you just decompile what this is, it just ends up being just this simple equation, right? Just multiply the matrix out. That's what you get. All right. So that's what a Bailey pair is. So a very simple Bailey pair is you just take alpha 0 to be 1 and everything else to be 0, and you'll just get the first column in that matrix. Yeah. And so that's the Bailey pair. That's one of the things you have, but it's very simple Bailey pair. It's not that useful. So we're going to get more useful Bailey pairs. Okay. So turns out that this matrix is invertible. Okay. So if you take the inverse, punch it in a Maple program or something, then the n equal to 3 row, which is, remember, it's the fourth row, because our indexing starts from 0, it looks like, I'll write it as a column because otherwise it wouldn't fit. It looks like this. Okay. Now it looks complicated, but there are patterns here to see. For example, you see that there is one factor of 1 minus a q to the 6 coming in. So you can immediately guess that that's going to be 1 minus a q to the 2n, n is 3 here. Or there is a factor of q that's in the front. It's not obvious here, but it ends up being just q to the triangular numbers. If you see deep down in the matrix, that's what happens. And then there are alternating plus and minus signs that you see in the front. Then you see a pokehammer in the numerator, a pokehammer in the denominator, and then there are zeros all the way. Yeah, it's again a triangular matrix, right? Because we are inverting a triangular matrix. Okay, so there is a formula for it. You look at it hard enough, you'll immediately see it. And you see all the points here, the alternating minus signs, q to the binomial, pokehammers, 1 minus a, q to the 2n, and whatnot. Right? So you see that something's a Bailey pair if and only if now I write alpha as m inverse times beta. Right? Because earlier beta used to be m times alpha. Now alpha is m inverse times beta. And now we can get actually a better Bailey pair. So what you now do is you just take beta 0 to be 1 and all the other betas to be 0. Yeah, and then you'll get, for alphas, you'll get the first column in this matrix. Yeah, so that's what is called a unit Bailey pair. Okay, so beta n is just delta n 0, and the first column, so you plug in r equal to 0 in this, and that's what you get for alpha. So that's a much more useful Bailey pair. So one thing to note is that this pokehammer an, it starts as 1 minus a, and there is a 1 minus a in the denominator, so they are supposed to cancel. In other words, this does make sense for a equal to 1. Okay. All right, so that's the unit Bailey pair, where you take beta to be 1 and all zeros, and then alpha to be whatever you get by doing this inverse. Okay, so that's the unit Bailey pair. And if I actually plug in a equal to 1, you get this Bailey pair. You just simplify it. It simplifies like so. And alpha 0 is 1. It's not clear. I mean, if you plug in n equal to 0, you don't get that. So I have to say it separately. Okay, so that's the unit Bailey pair with a equal to 1. You can substitute a equal to q, and you get that as the Bailey pair. Okay, it's literally just plugging in the things I said. Now, turns out this factor here that you see, it keeps popping up again and again. So I'm just going to introduce a new notation, alpha tilde, which just deletes this factor, okay, if I need it. So it's just going to delete that factor if I need to delete it. It just makes things shorter to write. Okay, so now let me tell you how to get the Rogers-Ramanujan identity using Bailey machinery. Okay, so start with a Bailey pair with respect to A. This slide and the next are going to be general. I think the next one. Anyway, so we are going to need to modify this Bailey pair. Okay, so this is any general Bailey pair with respect to a base A. So what I'm going to do is consider this diagonal matrix an and qn squared. Yeah, it's a diagonal matrix, and I want to change the alphas by multiplying this column vector of alphas by this d, and I'll get new alphas, alpha prime. And so in short terms, it is just alpha prime is an qn squared times alpha n for all n. Okay, let's see how that affects the beta. Okay, so of course, beta prime is, again, I'm not changing the base, so it's still m times alpha prime. So let's plug it in. Alpha prime is d alpha. Okay, so let me write it this way. And now note that the right hand is ma alpha times ma times alpha is our old beta. So it's just that. And I just have to figure out if there is a good formula for this, right? And again, I'm going to look at Maple, and it shows you this matrix. And there is a very obvious formula here. If you run down the columns, then you see A, power of A increasing, power of Q just taking squares. There is Pochhammer's coming in. There is obviously a formula for this. That's the simple formula. Okay. All right, so that means that this is how my beta is going to change. The new beta is this times beta. I'm now multiplying actually by that lower triangular matrix I showed you in the previous slide. And that's my new alpha, right? So I'll call this the first forward move. Forward because I'm enhancing the alpha by multiplying by A and Q. All right, so let's apply it to our unit Bailey pair. So remember, our unit Bailey pair had beta 0 was equal to 1. All other betas were 0. So only this r equal to 0 term is going to survive. Yeah, A is 1. So I just get beta 0 divided by this Q Pochhammer. R is 0. And if you remember, this is, okay, if you go back a few slides, you'll see that this formula is just, I took that unit Bailey pair and multiplied it with Q to the n squared. A is 1 anyway. Let's do it again. Yeah. Oh, this A should be a 1 here. But literally, I'm just plugging in this beta prime in place of this beta and getting a new pair out. And again, you see on the A side, I'm just multiplying it by Q to the n squared. So this 3n squared over 2 is just going to turn into 5n squared over 2, and rest all is the same. Yeah, so I got a new Bailey pair. This should have been a beta double prime. Yeah, because I have applied the forward move twice to the unit Bailey pair. Now let's write down the equation that actually asserts that this is a Bailey pair with the base 1. So that's the equation. Okay, so let's plug in what we have. So I plugged it in. Now remember, the formula for alpha double prime was a little different for 0, right? It was 1. It was defined a little differently from the general case. So I'll just pull out the r equal to 0 case. Yeah, that's here. And the rest of the cases are here. So that's just that. Let's take n equal to infinity and going to infinity. Then this is going to turn into a Q infinity Pochhammer. Yeah, this is going to turn into, you just do it. It's simple now. Cancel the factors. Yeah, and now you have to know what a Jacobi triple product identity is, which is the denominator formula for A11. And the right-hand side clicks into being a product, right? And the left-hand side is exactly our sum side, right? So that's Rogers-Ramanujan, if you remember. Okay, let me summarize what I did. Before that, I'll tell you what the Jacobi triple product is. So that's just that. It turns an alternating sum into a product. This is the denominator formula for A11. So obviously, what's going to be important for us is the denominator formula for A22, which is the quintuple product identity. I'm going to call it QT pi. No one got that joke, but it's okay. All right. So what is the summary? We start with a Bailey pair with respect to some base. We modify it, like I did, as many times as you want. Some of the moves may change the base. I didn't do that before, but I'm going to have to do it later. So we'll get some final Bailey pair, alpha n, beta n, with respect to possibly a different base, A prime. Now let's write down the equation that asserts that this new thing is a Bailey pair. And now, contrary to your intuition, when you take n goes to infinity, This is actually going to turn into a product. It looks like a sum, but that's going to turn into a product. The side involving betas is going to be the sum side, okay? Just like it happened in the Rogers-Ramanujan case, right? That's because alphas usually involve these alternating signs. I'll show you an example. And so when you click them into the JTP or QTPy, you get the product. Okay, so alphas are products, betas are sums. That's a thing to remember. All right. Are there any questions at this point? Because now all that I need to do is pick out judiciously the pairs, pick out the moves so that finally I get the characters. So that's really it. That's what left to do. Okay, if not, maybe I'll go ahead. Okay, so task 1, you have to choose the initial Bailey pairs judiciously. So you choose alpha and the base, then you'll get what the beta is. And remember, it's going to be important for us to choose the alpha because we have alphas are going to turn into the products and we have products are at our disposal. I don't really know what the sums are going to be. It's important for us to choose the alphas and the base judiciously. Then make a smart choice of those moves. I have not included a slide here, but you have a lot of guidance on how to choose these moves. You have to look in the old papers of Bailey or Andrews or McLaughlin and Sills, and you pretty much have a hint of what you need to do. But still, a lot needs to be done more. And finally, you just apply the quintuple product on the alpha side to get the characters. Okay, so let's see. So I'm just going to give you a sample of these moves. It's going to look a bit complicated. So I don't, I mean, the intention is not to give you all the details, just to tell you what variety there can be. Okay, so there are a few moves that are important for us. So as I said, this was a forward move, the first one, yeah. I enhanced the alphas. And now if you do the inverse of it, yeah, instead of enhancing the alphas, you sort of diminish them. Then you get what is called a backward move. And again, you figure out the formula for beta by pretty much experimentation. There are better tools available, but of course you can pretty much convince yourself that's going to be it by putting it into Maple. There's another forward move that's important. Again, here I'm somehow enhancing the alphas by putting in now a little bit different thing here. There are also poke hammers coming in. And there is a corresponding backward move where I just exactly do the opposite. So if you compose the forward and backward moves, you don't change anything. That's the point. Yeah. So there are 2 forward moves, F1, F2, and 2 backward moves. So they enhance the alphas a little bit. There is also a base change move. So you start with a Bailey pair of a base A, and you get a Bailey pair with base A Q inverse. That's what it's important. There are 2 of these, and these are a little bit complicated. So here's that alpha tilde notation that I said I might use once. Remember, there was that factor of 1 minus a q to the 2n divided by 1 minus a that I said will keep popping up and I need to delete it. It keeps up coming here, and so I need to delete it. So anyway, this is the first base change move, and that's the second one. So I start with a Bailey pair, and I will get, with these moves, a new Bailey pair with a different base. And you will see that things like this do come up in the product side when you try to write them down using the affine while group. Things like this, not exactly this. So it's a task to do to how to match these things. Okay, so these moves have been used by McLaughlin and Sills to get principal character of 1 module at every integrable level, but we want all of them. So turns out we need one more move, which fixes the Bailey pairs that are known. And it's called the base shift move. Okay, so what is it? So Jeremy Lovejoy let us know later that this was, and Chris Jennings Schaefer also independently told us later that this was actually a move that was discovered by Lovejoy 2 decades ago almost. What you need to do is start with a Bailey pair with a base A. You keep the betas, but get new alphas with a shifted base. Okay, so let's see how that plays out in our matrix formulation. So our new alpha is just going to be well, I want the base to be AQ. So it's MAQ inverse of the old beta. Yeah. And remember, the old beta was just M times alpha. So all that I need to do is now figure out a formula, if there is one, for this matrix. And there is one. It's a very simple formula. You do all that process I told you, and you get this as the formula for new alphas in terms of the old alphas. And again, I don't want to keep this annoying factor always, so I'll delete it. So instead, I'll just say alpha tilde prime is this easy sum. Okay. All right, so we have forward and backward moves, we have base change moves, and we have a base shift moves. So we are going to use the base shift to begin with. We'll take the Bailey pairs that are known in the literature, we'll change them, and then we'll use the other moves. Okay, so these are the Bailey pairs. As I said, the alpha part involves alternating things. So you see a minus and plus and minus. Yeah. So that's the alphas in my Bailey pair that I want. These are the betas. Yeah, they involve pokehammers like what you now know. And some of these pairs are with respect to the base q, and some are with q squared. There's a nice pattern here. If you're with base q, then it turns out that your 3n plus first alpha is 0 always. If you are with base q squared, then okay, I'll just close the window just a second. Sorry about that. And if you're with base q squared, then the mod 2 alphas are going to be 0 and so on. And this column tells you that these are modifications of the old Bailey pairs that were known. So the first 4 were known to Slater. This P1 is a Bailey pair that was known to McLaughlin and Sills. And the last column is going to tell us which identity it's going to give us later. So this is it. These are the Bailey pairs that we use. Our formulas here that I give are much nicer looking than the formulas that you see in this literature because we have modified the Bailey pairs now using the base shift. So I'm going to need 3 sets of moves to apply. Again, just to give you a flavor, what it looks like is the following. So what I'm going to do is I'll be given a k, which is at least 1, and an I. So what's going to happen is at the end of the day, all our modules, so remember at A11, we had 2 families, Gordon-Andrews and Andrews-Bressoud. Yeah, odd levels we got Gordon, even levels we got Andrews-Bressoud. At A22, we are going to get 6 families, okay, based on the level mod 6. And so roughly within each family, I need a parameter k, which is roughly going to be level divided by 6. And within that level, I is going to enumerate for me the modules. Yeah, so I enumerates the modules, k is roughly the level in that family divided by 6. And then we put together some moves, right? So if k and k minus I is bigger than 0, you use a forward move a bunch of times. If it is negative, you use the backward move a bunch of times. Then you go ahead and use the base change move. Then you go ahead and use the forward move a bunch of times, noting now that the base has changed because we use the base change move and so on. There is a second set of moves that we need. Again, it's some description. At the moment, it doesn't matter what it is. But yeah, it's again, you're putting these moves together in a very judicious way to get the required characters. And there is a third set of moves. Again, it's the same heuristic. K is going to count level divided by 6. And within each level, I is going to count the modules. And again, it's some set of moves that you're putting together, like constructing a toy based on your pieces. And so let's put everything together now. And this is the big table that I end up getting. So let me explain what this table is, because this is the key to everything. So remember, I had 5 Bailey pairs. These came from modifications of known Bailey pairs. So those are the in first column here. I have reminded you of their bases on the second column. So first pair had base q, second had q squared, third had q, and so on. Now, each Bailey pair is relevant for a certain level. So if you look at level 6k plus 1, remember I told you there are 6 families of levels based on the modulus, based on the level modulo 6. So 6k plus 1 level, it's going to be explained by pair 1. And if you remember, there are roughly half as many modules at a level. So roughly there are 3k plus 1 modules at this level. And as I said, I is going to enumerate the modules for you. So the I is going to go from 0 to 3k in this case, for example. So you get 3k plus 1 modules. And again, remember, the modules actually are determined by 2 integers, S0 and S1. The level is S0 plus 2S1. So I want to tell you exactly which module I'm talking about. Well, it turns out you take S1 to be equal to I, and that's the module I'm talking about, okay? So I gave you the moves. They depended on a K and an I. The K is corresponding to the level here. The I is the module. So depending on the module and the level you have to use certain moves that I gave you in this column. Make sense? Okay, now obviously there is a huge amount of information here. So let me just tell you a few things that are coming out of this. Okay, so first of all, if you look closely, if you have the base q, then you are using either moves in set 1 or 3. If you have base q squared, then you are using moves in set 1 or 2. That's always the pattern. Okay. Now, for a level that is not divisible by 3, okay, so either 6k plus 1 or 6k plus 2, 6k plus 4, 6k plus 5. Let's start with 6k plus 1. Each module is going to be explained separately by 2 different Bailey pairs. Okay, so there is this first pair with base q that explains it. The second pair with base q squared that explains it. But look at how they enumerate the modules. The first pair enumerates the modules in one way. The second pair enumerates the modules exactly in the opposite way. Yeah, because S1, which is one of the characterizing integers for the module, is 3k minus I now. Okay, that holds for 6k minus 1 as well. It's explained separately by pair 3 and 4. Again, same phenomenon. One enumerates the modules this way, the other one the opposite way. For 6k minus 2, you need these more complicated sets of moves, 3 and 2. But it's the same phenomenon, q and q squared. 2 different pairs explaining every module independently. Again, one going this way, one going the other way. Same with 6k minus 4. But if your level is divisible by 3, that is either 6k or 6k minus 3, then you are explained by exactly one Bailey pair every module. Okay, so let me go back one slide and I'll show you something. So here, this is the last Bailey pair is the one that explains the levels that are divisible by 3. And you see that it's different from the other pairs. In other pairs, you see a quarter of a factor in the exponent of q, but here it's only half. So there is a little bit of asymmetry in these pairs. Maybe that's what's going on. Okay, so that's one pattern. Actually, those are all the ones I said. And I don't think this much structure has been illuminated before, even in the in this context of Bailey pairs giving you some sides. Let me just show you some examples now. So with Rogers-Ramanujan at level 2, remember this was a dilated Rogers-Ramanujan. I said q goes to q squared. If you use the third pair with sets of moves in set 3, that's a equal to q, then you get this sum side. I don't think this is new. It was probably known to Slater in some form. I think this one was known to Slater. This one is the other Rogers-Ramanujan. This one looks a bit new, but I have not tried to see how it relates to the actual identities given in Slater's list. If you actually use the fourth pair for the same, getting the same Rogers-Ramanujan, and now its base is q squared, then you get these two sum sides. Now it'll take you more than a few seconds to realize probably that the first sum side is the same as the one I showed you before, and it'll only take you a few seconds because I put them in different slides. If I put them one after the other, you'll probably recognize it immediately. But anyway, the second sum is definitely different, right? Because it's only one sum, but here it's a multi-sum. And the reason this is a weird J1 and J3 is because there used to be a J2 there, but you can simplify it. All right, so that's a Caparelli example. So I think I'm almost there. I think there is only one slide left. So this is Caparelli. So the reason I've put this in orange in previous slide as well is because those are coming from the Bailey part. So this is the beta in the Bailey pair. And I think these are new. These sum sites are new. I haven't heard of anyone having discovered them. But maybe they are related to something I don't immediately know. So what is left to do? Well, obviously now we understand A11, that was done decades ago. We now understand A22. What about the higher rank? Second thing left to do is I still don't know how the affine while group is exactly related to the Bailey pair. So that's something that'll be very nice to illuminate so that we can guess Bailey pairs and the Bailey machinery for higher ranks. And thirdly, what are these sum sites counting? They don't always count the things. Rather, let me put it this way. They seldom count the things that are going to be coming from actually counting the bases. They usually count something different. But still, we don't know what these count beyond, I think, level 7. I don't think there is any description. And that's it. Thank you.
Thank you. So I'm going to turn off the recording so that we can ask questions.
Thank you. Yeah.